Hello everyone, my name is Nanning Li. Today we are going to talk about the introduction to reinforcement learning. This is the content we are going to cover today. What is the reinforcement learning and the applications for the reinforcement learning. We're going to talk about a mathematical model to describe the RL problem, and in the end we're going to have some definitions for the value function and the Q-value function. So what is reinforcement learning? So this problem involves an agent interacting with the environment. So the environment will give a reward based on which action is taken by the agent. And the goal is to maximize the cumulative reward. So the reinforcement learning has many applications. For example, this one, the robot locomotion. So the aim is to make the robot to go forward and to basically walking. So we have the status basically. Imagine a robot have many degree of joints. So the states would basically be the angles and the position of the joints. And what we're gonna do is every joint has a motor. You can the motor need to apply a torque to the joint, which can make the robot move. So the action basically is torque applied on the joint, and the reward is for each time step. We can actually make the robot to move forward. And another application is the computer Go. So maybe you already heard about that. The computer Go developed by the DeepMind actually be the world championship in that game. Right now, by using the reinforcement learning. So the performance of using that reinforcement learning method in the computer Go is amazing. It's a little bit, I will not talk about that in details, but essentially, so the goal is very obvious, to win the game. And the state is, okay, how the position of all the pieces, how my black and white pieces are located on the board. And the action is how you actually make the next move, how you actually put, for example, if you're holding the black piece, how you actually gonna put it for the next step, according to the current state. And the reward is, okay, if you win or not. So there are some other reinforcement learning applications. For example, the carpal problem, which is a very classic control problem. And archery games. I mean, a lot of people probably have heard about that. You played that probably during your childhood and investment portfolio. So you can actually use the reinforcement learning to maximize your profit, to maximize your profit based on in the stock market, based on the current state of the stock market, and so on. There are so many applications you can use the reinforcement learning method to solve. And for the reinforcement learning, you can actually use a mathematical model to describe the problem and how. So we actually gonna use a model called a Markov decision process. A Markov decision process is a mathematical formulation for the reinforcement learning problem. And obviously, it has a very important property called Markov property, which essentially is that you make the decision only depends on the current state, not based on the previous actions you have taken and the states you have gone through. So the current state already describes the whole information you need. That is a Markov decision, and mathematically you can describe the Markov decision by a set of possible states, a set of admissible actions, and the distribution of the reward given the current state action pair, and transition probability, how you actually go from the current state to the next state by a probability given by described by the transition probability, and the discounted factor. The discounted factor here is that you care more about the reward if you reach the current state. However, you care less for the future reward. Basically saying, okay, however, this discounted factor can be 1, meaning, okay, I value as much I value the future reward as much as the current reward. This can be in some applications, for example, safety applications. So you will not say, okay, I care less about the safety in the future. So how actually the Markov decision process works? It basically described here. At the time step 1, at time step 0, the environment samples an initial position. So basically say, I don't know where we are. We have an initial distribution, which is sample 1. And at the time 0, we start the Markov decision process by taking an action AT. And the reward is based on the current state and the current action you've taken. For example, if you have reached the goal, you get a reward 1. And if you haven't reached the goal, you get a 0. If you hit the obstacle, you probably can get a negative reward. And so like I said, the transition probability would describe how much chance you can actually reach the next state, given the current state and the current action. So after done that, the process repeats until either you time out or just keep going, which there are many different settings for the reinforcement learning. For example, infinite discounted horizon problem, or finite horizon. So there are many ways. So in this one, for the reinforcement learning, we are trying to find a policy. A policy is basically is a mapping from state to action. So it's basically intuitively it's a function. The parameter is the state, and output is the action. So you are trying to just plug in the state. You are trying to compute that function, and you when it runs on the robot or whatever agent is, you just plug in the state, and it gives out the action. And it is well known that for the MDP, the Markov decision process, there's always a stationary policy. You can always find that optimal policy. So stationary meaning the policy is independent of the time. And the optimum policy, we are trying to find the optimum policy, which maximize the cumulative reward. Meaning, okay, I want to reach a goal. the goal gives 1. Or think about a shortest path problem. I want to go to, for example, from my home to the school in the shortest distance. How? You can give a negative reward by taking 1 step. And you want to try to find a policy by saying, okay, go straight, go left, go right, and you will find a shortest path eventually by doing that. And think about that. In our Markov decision process, we have the transition probability to describe the stochastic system, meaning the transition is not deterministic. How we actually can capture that, the probability. In probabilistics, we already know that we can actually use the expectation. So the expectation can actually capture the initial state, the transition probability. So we actually, in our problem, in reinforcement learning, we try to maximize the expected sum of reward by using the expectation to capture those randomness. Now I will give a very simple example about the MDP, a reward. So everything here is not continuous, it's discretized. So think about that. A robot wants to go to the star, which is the goal position, and try to avoid the fire, which is a very dangerous state. So the action here is the robot can go right, go left, go up, go down. Only 4 actions. And the objective is to reach the goal in the number of the actions, in the least number of the actions. So what we can do is that, the objective here, if I set the reward here is like this, the objective here should be just reach the goal. In the what we are trying to do, the reward here is if we set the goal as 1, and if the robot reach the fire, it gives the negative. So by doing that, the reinforcement learning method would enable the robot, the agent, to reach the goal while avoiding the obstacle or the fire autonomously. So this is a very naive, simple example, but this example is the prototype for many problems. So it can be used in the path planning, it can be used in the motion planning for the robot, for the humanoid robot. It has many applications. So here I will try to give you some definitions about the value function and the Q-value function. So the value function is actually the expected cumulative reward by following the policy from the state, and the Q-value function is very similar to the value function, which is that the expected cumulative reward by taking the current state, by taking the current action given the current state. And the next time, thank you everyone. And next time we are going to talk about how to actually find an optimal policy by using the Bellman equation. And we're gonna cover some method, which is model-free learning, like very basic value iteration and the policy iteration. also another model-based learning, Q value iteration. Thank you, everyone.